This meeting is being recorded.
In the last section, 10.5, we looked at radioselectivity of halogenation for both a kinetics or a thermodynamic standpoint. The kinetics, which reaction was faster, and then thermodynamically, which product would have the lower potential energy. So that was the radiochemical distinction that we looked at last time. Now we're going to look at stereochemistry. So if a chiral center is created or a chiral center already exists, we're going to have to consider what stereochemical outcomes will occur. So when we halogenate butane or higher, a more complex alkane, we can form a new chiral center. Anything smaller, we would have, two of the same functional group at our sites. So when we have butane here, the primary site, this would not produce a chiral center if chlorination occurred here, but at a secondary site, notice we're going to have 4 different groups on that carbon there. So 2-chlorobutane will form as a racemic mixture. So let's see why this happens. In an earlier section, we looked at the molecular geometry of a free radical carbon and whether or not we said it was sp2, which it seems to be most like, or if it was a rapidly interconverting sp3 shallow pyramidal trigonal pyramid, we would get a halogen abstraction or removal of hydrogen on either side of this carbon, so either side of the plane rather, with equal probability. So that's where we end up with S and R configurations in a racemic mixture. So this is the Y, and this is what happens here. So say we have chlorination, halogenation of butane here, specifically chlorination. What could happen is we get the primary site chlorination here and a single product that's returned, and then we get a racemic mixture, both R and S in equal quantities of these two configurations, these two stereo isomers. So in the previous example, in this example here, there were no chiral centers, so none to start with. So no chiral centers to start. But what we see here is you can either create a chiral center or you can have a racemic mixture happen if we already have a chiral center. So this carbon here at the chiral center is the most reactive site because it has the weakest CH bond. Therefore, the tertiary carbon will be the site where bromination occurs. And we have this S3 methylhexane as our starting material here, and that chiral center will be brominated, and we would obtain a racemic mixture of both the S and R brominated species. So we will continue with section 10.7 in our next video.